and this, and this. Okay, guys, so here's the topic for your notes today. And Brandon, you may recall last time you asked a question about what's up with Spectra. We're going to talk about it right now. So, guys, in order to make this segue, if I can use that term with you, in order to make this segue, what I'd like to do is I'd like to take us back to this picture. So, why is the concept of quantized energy important? Well, again, the observation was atoms release photons that have energies that are definite. We don't see all energies, we see some energies. And again, the brilliance of what Bohr did is he said the only thing that could explain that observation is that unlike the the Thomson model that says electrons can be anywhere, Bohr interpreted that to mean there's places where electrons can't be, and there are places where electrons can be, and that then became the planetary model of the atom. Now, guys, the transitional thought then goes like this. First of all, how do we experience, and I mean this quite literally, how do we see with our eyes? How do we see that some falls are allowed and therefore those energies are emitted, and some falls are not allowed and therefore those energies are not emitted? How do we see this? And the answer is spectra. And that's what I'm about to show you. But guys, before we jump into spectra, what I'd like to do is I'd like to tie this back to the way that we're going to end the day. So guys, I think from our previous conversation, you're comfortable with this idea, but let me make sure. Why can this atom, the one on the right, why can this atom not release a 1 joule photon? There's no falls that represent a difference of 1 joule. Does that make sense? You're okay? Okay, but now, guys, let me back this up one more step. And this is kind of an obscure question. What is it that allowed us to make that observation? And guys, the answer is this. We knew the energies associated with the energy levels. If we didn't know that the first energy level was a 1 joule energy level and a 3 joule and a 7 joule and a 14 joule, if we didn't know those numbers, we wouldn't know the energy changes associated with moving between them, and therefore we wouldn't be able to figure out what drops were allowed. Does that make sense? Okay, because guys, as soon as we're done talking about what spectra are, we are then going to talk about how do we figure out the energies of the energy levels. Do you see where that's headed? And once we can identify the energies of the energy levels, we can then figure out the energy associated with the electrons going between them, which will then allow us to figure out frequency and wavelength and color and all that other stuff. That's the big picture for today. You ready to go? Okay, so first of all, we understand this. When these electrons fall, there are energy changes associated with those falls. Those energy changes are directly related with frequency, E equals hv, h nu, and those are also associated with wavelength and color. So what do we see then related to that color? Because what we see are what are called spectra. And guys, they look like this. Obviously, don't try to write them down. But guys, there are 3 different types of and absorption spectra being opposites of each other. Here's what we're talking about. So, guys, I think that you understand that if you take light and pass it through a prism, because light is composed of energy with different wavelengths, those wavelengths of energy interact differently with glass. The longer the wavelength, the more the wave will bend as it travels through another medium. That's why our sunsets are red. Did you guys understand that? Should we talk about it really quickly? Guys, that's why our sunsets are red. When the sun sets, imagine that this is the earth, and imagine that this is you standing on the earth, and imagine that this is the sun, and the light from the sun is hitting our atmosphere. Okay? What happens is when the sun goes down, what's simply happening is the sun is dropped low enough on the horizon that the light goes right over your head. But it turns out that our atmosphere operates like a prism. And so as the light travels through our atmosphere, the red light is bent more and the violet light is bent less, because red light is longer wavelength than violet light. And so as the sun drops below the horizon, the last light for us to lose is the light that was bent the most, and that's the red light, and so consequently our sunsets are red. Okay, so guys, with that said, the same thing is going on here inside of Spectra. You take light and pass it through another medium, in this case glass, and the wavelengths of energy that are longer will be bent more, the wavelengths that are shorter, the violet, will be bent less, and it spreads the light out into what we call a spectrum. Well, guys, there are three kinds. If you take white light and pass it through a spectrum, you get all the colors of the rainbow. Because, guys, white light actually doesn't exist. White is not a color. The only reason white light exists is because our eyeballs get overwhelmed with all the energy that they're absorbing from all the colors of the rainbow. And we've been trained since we were infants that that experience is called white. Guys, white is not a color. White is actually all of the colors of the rainbow mushed together, shot in our eyeballs, and our brain takes all of that information and says, let's call it white. White is not a color. So, we now understand that white is all the colors of the rainbow put together, the visible spectrum. Well, guys, what happens is this. If we can take any particular, what would be a good color to write in? Maybe blue. I think that'll show up. So guys, if we can then take an elemental gas, it can also be molecules as well, but we don't have to talk about it. If we can take an element, say for example, hydrogen, and if we can take these hydrogen atoms, and remember there are electrons moving around the hydrogen nucleus, if we can take those hydrogen atoms and if we can excite their electrons, and guys, how do we excite electrons? How did you do it last year in lab? Bunsen burners, right? The flame test lab. In this class next week, we're going to use, 7,500 volt power supplies. But what we're going to do is we're going to take these electrons and we're going to excite them, and they're going to jump up to excited states. And then once they can, those electrons will fall down to their ground states and they'll release light, right? But what you'll find out is that if you can take that light that is released by falling electrons, and if you can break it apart into each of its colors, you will find bands of color, and then you will find places where those missing colors are not emitted. So guys, the question is why? Why are some colors emitted and why are some missing? Go ahead, Brandon. Do you get that? Guys, the answer is because in this atom, there are some places where electrons can be, and there are some places where electrons can't be, and as a result, not all falls are possible, and consequently, not all colors are possible. Yeah? No, some of this stuff we don't even see. Some of it's infrared, Some of it's ultraviolet. I mean, it can understand it can't be gamma to radio because of the limitations of the mass of electrons and their velocities. But no, it's not all visible. It can be outside, not far outside the spectrum, but it can be outside the spectrum. Yeah. Yeah, absolutely. Yeah, actually, a lot of it now is ultraviolet. I don't know if you've ever seen that. It's actually really cool. Our special forces right now, as they're moving around, they actually have, they have light. Well, they actually have ultraviolet glow sticks. And when they go into spaces after they've cleared them, they'll actually drop these UV glow sticks. And the only way they can see them is with their visors. And so the enemy can't see that they've been there because the thing doesn't emit visible light. But they can see and they know they've been. It's pretty cool. Anyway, so yeah, our military is pretty cool. So guys, let's translate. Okay, so that color, if you will. What do we know about the electron that emitted that color? Didn't fall very far, right? Short fall, low change in energy, long wavelength, low frequency red light. What do we know about these dudes? Long falls, right? But guys, what these colors, and let's make the connection, what these colors really represent is this. If we know the color, we can figure out the wavelength. If we know the wavelength, we can figure out the frequency. If we can figure out the frequency, we can figure out the energies. Matt, don't. We can figure out the energies. Once we know the energies, we can take those backwards and we can figure out the energies of the energy levels where they fell from and to. Get the idea? So guys, that's what we're going to do today. And then just very briefly, guys, we don't have to do absorption spectra, but the idea, because you asked Brandon, we'll talk about it quickly. If we could take this same gas that's emitting the light, and if we could cool it off and pass white light through it, what happens is the same electron falls that were happening in the hot gas turn into electron excitations in the cold gas, and the same amount of energy that is emitted when they fell is absorbed when they excite, and you can actually get what are called absorption spectra by passing white light through the same clouds of gas. And if we're absorbing energy, the energy that is absorbed will be exactly the opposite of the energy that's radiated when they fell. Get the idea? That's what makes astronomy so hard. Because guys, how do we know what stars are made of? We take the light from the star, we pass it through a spectrum, and by looking at the spectra, we can figure out what elements are up there by knowing the spectral signatures of all the elements. But here's the problem. Many times that starlight from the hot gases in our stars don't travel unimpeded to Earth. They can travel through clouds of cold gas. And those cold gases can actually filter out some of the wavelengths that the star had initially emitted. And it becomes an amazing guessing game to figure out what stuff is up there quickly. And it all redshifts. We're not going to talk about what that means, but basically what happens in starlight is all of these lines shift in that direction, which is actually an amazing supporter for the idea that our universe is expanding and therefore banged. Okay, so guys, I know this is going to kill you, but we're not going to take notes. We're just going to talk about this because this is the stuff that you guys all seem to be comfortable with. So guys, most of the light that we deal with contains many wavelengths, and we can separate these by passing them through prisms into spectra, of which there are 3 types that we just talked about. Now, what we do is we deal with line spectra. And this is now the third time we've talked about the idea that line spectra are created by taking gases, exciting them. In lab, we're going to use high voltages. And when they do, they display the wavelengths of light that is emitted, separated by black spaces that represent missing wavelengths. Now, guys, we know that those lines represent electrons that are making falls, and the black spaces represent changes that are not possible, right? So the question then becomes this: how do we know which falls are possible? Well, guys, in order to do this, what we need to know is we need to be able to quantify the energies that are associated with the energy levels. So functionally, what we're saying is this: if we want to be able to figure out that we could get a 2 and a 6 and a 4 and a 7 and an 11 and a 13 joule photon, we need to know the energies of the energy levels, right? We've got to be able to quantify the energies of the energy levels. Well, guys, I'm about to show you how to do that. You ready? Here we go. Write this down with me. This is the equation that allows you to quantify the energy of the energy levels. Ready? It is simply this: the energy of an energy level is equal to negative R sub h divided by n squared. That is a darn simple equation. Guys, sometime before the test, copy this onto your AP equation. Well, you know what? Do this. They took this off of the AP equation sheet. You never have to memorize equations, which means they'll never ask you to solve this equation on the AP test, but I will in this class. This is important. I can't believe they got rid of it. That said, because it's not on the AP equation sheet, I'll give it to you. So guys, here we go. What is R sub h? Well, let's first of all talk about n. N is the principal quantum number. What are the possible values for n on our periodic table? 1 through what? 7. We have energy level 1, 2, 3, 4, 5, 6, 7. Remember that magic day last year when you found out that this was the S, this was the P, this was the D, this was the F sublevel? And then you found out that we've got energy levels 1 through 7 that are broken into sublevels SPDF. And then we said that the first energy level contains an S, the second is an S and a P, the third is SPD, and so on. Guys, those numbers, first, second, third, fourth, fifth, sixth, seventh, are the N values. So now what about R sub h? Well, guys, you're going to find out that R sub h is what is called the Rydberg constant, but you need to know right now that its value is 100 joules. So now, guys, do this with me, and I would really encourage you to do this. Draw an atom. And if you would prefer, and we're only going to go through energy level 5, we could go to 7, but hey, you could do this. You could just do a nucleus, and then if you like that idea of just drawing the arcs, I think that's legit. But guys, I chose to write it all out just to make sure you've got the concept. We do, of course, understand this is not what atoms look like. We've got the one S, and then the second is made of an S and P, and the third is SPD, and so on. But we're going to let them be represented by rings. Okay, so now, guys, we're going to plug in some numbers. You ready? Let's figure out the energy associated with this first ring. So to do that, we use this equation. We plug in the Rydberg constant, 100 for R sub h. We plug in 1 for n, and we have negative 100 divided by 1 squared, which is what? Negative 100. Write it down. We now know the energy of the first energy level. It's negative 100 joules. Now let's go to the second energy level. Again, negative R sub h is always negative 100. Is negative 100. Now let's plug 2 in there. 2 squared is 4. 100 divided by 4 is, right, but it's negative 25, right, because R sub h is negative. So now, guys, let's go to energy level number 3. Energy level 3, 3 squared is 9. Negative 100 divided by 9 is functionally negative 11. We're rounding somewhat grossly. Now, guys, let's go to energy level number 4. Negative 100 divided by 16 is functionally negative 6. And then, guys, going out to energy level 5, 100 divided by 5 squared, which of course is negative 4. We'll stop there. So, guys, with this said, now that we finally know the energy of the energy levels, let's talk about what this allows us to do. So say that we've got an electron in energy level 3, and that electron falls to energy level 2. What will the energy of that photon be? 14 joules. So guys, why was that hard? Because the numbers are negative. So guys, let's talk about what that means that these numbers are negative. Don't miss this. This is critical. So guys, first of all, do this. And then we'll come back to this photon. Do this. Negative 100, negative 25, negative 11, negative 6, negative 4. What is the trend in those numbers as we go from the middle to the outside? Are the energies getting bigger or smaller? Bigger. Negative 100 is a smaller number than negative 4. So guys, as we move out, the energies are getting bigger. Stop right there. As we move out, the energies are getting bigger, yes? Yes, but you knew that. Because if an electron falls from 3 to 2, the energy of energy level 3 is greater than the energy of energy level 2, and energy comes out, right? You knew that is, and it's even further driven home. What would it take to take an electron and kick it from here to there? What do we got to do to make it move out? Add energy. So doesn't that mean that there's more energy up here than there is down there? Because we've got to add energy to get them to go out. Good? Okay. Guys, so we know that as we move out, the energy is greater. Here's the thing that makes this weird. The energy gets greater by becoming less negative. You may want to write that down. The energy becomes greater by becoming less negative. And guys, I hope you hate that. Right. Yeah, oh no, absolutely. Why can't it just get more positive? So guys, let's ask the bigger question. What on stinking earth is negative energy? It's like negative mass. Can you have negative mass? Can you weigh less than none? No. Can you have less energy than none? No. So what on earth is negative energy? Guys, don't miss this. This is critical. What on earth is negative energy? Well, guys, the thought is this. These negative signs right here don't mean less than 0. These negative signs are directional. Relative to what? The nucleus. So guys, you may want to write that down in your notes as well if you can't keep track of that. The negative sign on these energies is directional relative to the nucleus. Let me explain to you what that means. Let me do this. I got this from a colleague of mine up in Park City. This is the way he teaches it to his kids, and I like it. He says this. Imagine that this is ground level. This is elevation 0. You're 0 feet of elevation. I'll put FT. Now imagine you dig a hole, and that hole is 1 foot deep. What is your elevation now? -1 foot. How high are you going to have to go to get out of the hole? 1 foot. Now imagine that you dig that hole even deeper, and now you're down here 2 feet below. Well, that's a -2 foot elevation. How high are you going to have to jump to get out of the hole? 2 feet. And you guys understand where this is going. 3 feet, and so on. So guys, how can you be negative feet? You can't. What does the negative tell you? It's direction relative to a fixed point. Well, guys, the same thing is going on here. These negative values are relative to a fixed point. And guys, what is the fixed point? The fixed point is way over here. Guys, what happens, follow the trend. What happens if we were to go 6th, 7th energy levels? What are going to happen to these numbers? They're approaching 0. Stop. Yes? Is that okay? Do you see that these numbers are approaching 0? And guys, what does that mean when that electron finally approaches 0? So if this electron goes energy level 7, energy level 8, 9, 10, 11, 12, 13, what if that electron gets out here to energy level infinity? 0 what? 0 what? Attraction to the nucleus. And now the electron is gone and we just formed what? An ion. Does that make sense? So guys, let's say this again. How can it be that these numbers are negative? Because these numbers are relative measures of attraction. And when does attraction become 0? When the electron is so far away from the nucleus that it is no longer attracted and it is now gone, and we call that ionization energy. Get the tie back to question 31 from the homework? So guys, the idea here is that these energy values are negative up to a maximum of 0. And at that maximum of 0, the electron is gone and it's no longer associated to the nucleus. So maybe that would be another good thing to keep in your notes, is that these energies are energies of attraction up to a maximum of 0 when the electron is gone. Should I say that again? These energies are energies of attraction up to a maximum of 0 when the electron is gone. And we call that ionization energy. That does make sense? Yeah. Yeah, because that whole negative, did you like, was that helpful? Be honest with me, the whole thing? Okay. Right. So now from there, guys, can't we now do this? Let's go back to our electron. And if we've got this electron that's doing this, how do we figure out the energy associated with that electron? Well, we go change of energy is equal to energy minus energy. Is it initial minus final or final minus initial? Change is always final minus initial, right? So now, guys, let's do the calculation. Change in energy is equal to, what is our final energy? Negative 25 joules. Minus, what is our negative, and what is our initial energy? Minus 11 joules, but negative 25 joules minus a negative 11 joules is functionally add, and so that would then be negative 14 joules. That's the point. What does the negative tell you? Energy is being radiated. In what form? Light. Yes? Do you see it? What are you going to screw up on the test? You're going to screw up signs. Guys, always, always, always. And I'm going to final minus initial, and don't get cocky, kid. Make sure that you're keeping the signs on the numbers. And again, as Catherine pointed out initially, what is the significance of the fact that the number's negative? It's being released. So we know that as this electron goes from energy level 3 to energy level 2, it is releasing a 14 joule photon, and then we could go energy to frequency, frequency to wavelength, and we can have all the fun with that we want. You get the idea? Go ahead.
So it's our system, the atom, so.
Yes. Yes, and more specifically the electrons. But yes, you could think of the whole atom. Yeah, so when you're defining system and surroundings relative to signs, our system is always the atom. Go ahead, just a second, go ahead.
You only have 7, right?
No, and this is where this gets really interesting. First of all, this boundary, did you guys hear Ethan's question? I assume you meant rings, energy levels. He said, can you only have 7? And the answer is no. We can actually excite electrons into energy level 8, 9, 10. How do we know that we can do that? Because we see spectral signatures that can only be explained by electrons falling from energies 8, 9, and 10. Because they're still associated with the nucleus. So how far do we have to push them in order to get them to break off? All we would have to do is know the ionization energy of that particular atom and work it backwards to figure out which energy level that's associated with. Yeah, but so Ethan, finishing your question, is it only up through 7? The answer is no. So what about the tie back to the periodic table? Well, the only energy levels that we see populated in naturally occurring elements in their ground states is up through energy level 7. But we can take those electrons in energy level 7 and we can excite them out into 8, 9, 10, 11. It just keeps going. But the bounds that we find important is energy level 7 and then energy level infinity, which energy goes to 0 and then it's gone. Does that make sense? Okay, go ahead.
So when you're like trying to get the electrons to fall,
Yeah.
do you always have to excite them, or is there any way to extract energy from them in the ground?
No, that's a good question. Catherine's question is, can you get electrons to fall without first being excited? Is that fundamentally it? Yeah, so you learn about this in college more, not relative to atoms, but relative to molecules, because you're going to find out, it's horrible stuff. You're going to find out that not only do atoms have electron structures, so do molecules. And you talk about things that are called HOMO and LUMO. HOMO is the highest occupied molecular orbital, and LUMO is the lowest unoccupied molecular orbital, but it applies to atoms as well. There's a fundamental principle that says an electron cannot fall into an orbital that is full. Okay, but in order for an electron to be in its ground state out here, we know that all the underlying orbitals are full. And as a result, those two ideas tell us that you can't have an unexcited electron fall, because there'd be nowhere for it to fall to, because all the inner structure is full. Yeah, go ahead. Yeah.
So, I was in that one class that showed
Yeah.
us the levels can keep going on forever.
Yes.
They get more scrubbed.
They do. The distance between them actually changes. So we can figure out the radii of these. Well, here, let's do this. So, you know what? Forget what I was about to say. So what Brandon is saying is this, that if you were to look at the actual distances between energy levels, it would actually look like more like this. They actually are becoming ever closer to each other. But check this out. Look at these differences. What's the difference here? 75 joules. What's the difference here? 14. What's the difference here? 5. What's the difference here? 2. Yeah, these energies, the distances are synonymous isn't the right word, but I don't know what is. They follow in step with the energies, and these because it's n squared, the energies are all the difference between the energies is always decreasing, and consequently the distance between the energy levels is always decreasing as well. Yeah.
Is it right to say like the reason why that electrons are in different shells
Mm-hmm.
is just because like electrons don't like being close to each other, or
No, it's what you're saying is not wrong, but it's also not the explanation. So why do these electrons ultimately take on these spaces? And the answer can't be answered thinking all of this that we're doing, we're thinking of electrons as particles. In order to understand why they do this, it can only be explained mathematically by describing electrons as waves. And then what you find out is that the maxima in their waveforms predict these structures. But we're not going to get into that. So, guys, we are, however, going to move forward. So, don't hate me. But, guys, here's the deal. This is not the value for the Rydberg constant. If I had told you what the Rydberg constant actually was, you'd have been so caught up in that number that we could have never had this conversation. So let's actually talk about what it is. It's this. The actual value for the Rydberg constant is 2.18 times 10 to the negative 18th joules. That's right. Take that out of your notes. But guys, you do understand the important scientific principle. If you understood the math based upon 100, you get it for this. Because guys, you understand this, right? Is this number positive or negative? It's small, but it's positive. It's 0.00017 but it's still positive. It's just not 100, so it's not as fun to play with. No, we got to go. So guys, this is what we can then do with this. We can solve problems like this. It says this. Calculate the wavelength of light that corresponds to the transition of a hydrogen electron going from the fourth to the second energy level. So guys, now we need to talk, because when you get into your homework, you're going to hear this mentioned a lot. This idea of a hydrogen electron. Guys, that equation that I gave you, negative R sub h divided by n squared, only works for hydrogen. What is so unique about hydrogen? It's got one electron. If you want to talk about helium, you need much more complicated equations. How come? Because those two electrons push on each other. The only thing that our equation has to account for is one electron being pulled on by one proton. Guys, since then, we've been able to develop equations that describe multi-electron systems, but the only one that we're going to do this for is hydrogen. Understand the difference between hydrogen and all of the other elements, the multi-electron elements, isn't much. So in lab, we're going to use this equation to apply to other elements. But fundamentally, technically, this only works for hydrogen. So guys, how are we going to solve this problem? How are we going to figure out the wavelength of light when an electron goes from the fourth to the second energy level? What does that calculation look like? Well, if we want to know the wavelength, what do we need to know first? Well, we need to know the frequency. And if we need to know the frequency, what do we need to know first? The energy. So how do we figure out the energy of this photon? Well, we know that it's going from the fourth to the second energy level. So can't we say this? That the energy change, which will be the energy of the photon, will be energy minus energy. But it's final minus initial. And guys, what is our final energy level? 2. And our initial energy level is 4. So the math goes like this. I can never remember the value for R sub h. What is it? So negative 2.18 times 10 to the negative what?
The exponent's negative.
Okay, hold on.
The equation was negative. 10 to the negative.
No, you guys are confused. So, negative R sub h divided by n squared minus a negative R sub h divided by n squared. Now I'm going to work to the left. So R sub h is 2.18 times 10 to the negative 18th? Oh, good. So negative 2.18 times 10 to the negative 18th joules. All of that divided by 4 minus the quantity negative 2.18 times 10 to the negative 18th joules. All of that divided by 16. So we need to do that math. So I'll put down some intermediate calculations. 4.54 times 10 to the negative 19th joules minus a negative 1.36 times 10 to the negative 19th joules. So we have 4.54. Oops. So negative 4.54 times 10 to the negative 19th plus I got 3.18. Oh, little dyslexic. Tell me your number. 4.09 times 10 to the negative 19th joules. Can you guys confirm that? Am I okay? Okay, so guys, let's talk about this. What does that tell us? Well, now we know the energy of the photon. This is the energy of the second energy level. This is the energy of the fourth energy level. Aren't you glad that I used 100 the first time I taught this to you? Then, guys, when we subtract the two, that gives us the energy of the photon. And again, what does the negative sign tell us? It's being emitted. And then, guys, what do we do with this? Well, now that we know the frequency, can't we go wait, where are we going with this? We want to know wavelength. So if we know the frequency, we can just go C is, no, that's energy. Yeah, no. So if we know energy, we can go this is h nu. We can solve that for frequency, and then we can plug that in here, and we can figure out wavelength. You get the idea? Okay. So guys, those are the kind of calculations that you're going to be doing in homework. And then you're going to see that after the weekend, we're going to leverage some of these ideas, and we're going to tie this back to this idea of PES as well. So, all of that to say, there's your homework. That's correct. And you will never see it in AP.